So what we're going to learn how to do today is calculate some more complicated limits, and the first example I have is a little bit graphical. The first example we'll have after we go through the limit laws are graphical. So if you have a constant c, and you have two functions, and the limit as x goes to a of both of those functions exists, then you can find limits of related functions, and it's really quite simple. Like f plus g is found by adding together the y's of f and g, right? So if you want to figure out what happens as x goes to a of f plus g, you can just figure out what happens as x goes to a of f, and you can add on what happens as x goes to a of g. So the point is you don't have to actually add the functions together. You just find the limit of the first piece, limit of the second piece, and then add the resulting things together. And that's true if both limits exist. If one of the limits did not exist, then you couldn't find the limit of the sum either. Does that make sense? So this does rely on the assumption that both of these limits exist. And if one of them doesn't, then game over. And if that's true for addition, what do you think is true for subtraction?
Same thing.
Same, just a minus sign, right? Okay, and in part 3, c is a constant, so the function c f of x is obtained by taking the y values of your function and multiplying them by some number, right? So that's going to like maybe shrink or expand where the limit is, right? But it will be just c times the limit. Like that c can kind of factor out of the limit. And like in this one, the y's of the new function are taken by multiplying the y's of the two original functions. So you think, okay, I've got one y that goes to 5, one that goes to 10. When you multiply it, they're going to go to 50. So this will just be the limit of the first thing times the limit of the second thing. And can you agree that if 4 is true, number 5 is probably pretty similar to 4? Except for there's one slight complication, and it's quite slight. So it'd be limit as x goes to a of f of x over the limit as x goes to a of g of x, except the limit as x goes to a of g of x, what can't that be?
0?
Yep, it can't be 0. So in that case, the restriction is that limit of as x goes to a of g of x first has to exist and be a number, and the number that it goes to can't be 0.
Right.
Which is the same thing as the same rule for like anything else as a denominator, right? So.
Well, couldn't you just take a limit of the limits?
Could you take a limit of the limit? When you so not yet. I mean, if the denominator goes to 0, occasionally you can do some messing with it algebraically, and then you can figure out that it actually goes someplace. Yes, but without knowing more information, there's not like a general thing I can say. Okay, so let's use those things with a picture. Now, I think the picture on your notes doesn't come through color-coded, but in your book it's actually color-coded. Nope, not in mine. Okay, so there are two functions here. They're f and g, and I'm just going to trace over f in purple, so you can tell which one f is. And it's more or less clear from the labeling who's who, right? Ish. Okay, so we're going to find the limit as x goes to -2 of f of x plus 5 times g of x. So using those properties, we can make this into the limit as x goes to -2 of f of x plus 5 times the limit as x goes to -2 of g of x. That officially used what two properties on that list? The first and the third, exactly. Okay, and then nothing has changed from yesterday. So as x approaches -2, this is x equals -2 right there, right? So what's happening to the f, or the y value of that f function, as x gets close to -2 from both sides? It's going to 1. Even though that dot is filled in up there, if your worldview is just getting close to but not equal to -2, you're getting close to 1, even though there is that jump. So you don't know, like, because you're only close to -2, you don't know what happens at -2. Pretend it's like something that's not in your field of knowledge. How about g? -1. And so then the result there, I believe, will be -4. Okay, this, we would want to say that the second one was the limit as x goes to 1 of f of x times the limit as x goes to 1 of g of x. Can we do that?
No.
No. And I want just a short reason why you can't do that. Which one is causing the problem? Is it f or is it g?
G.
G. So no, because the limit as x goes to 1 of g of x does not exist. And the reason that the limit doesn't exist there is because of this jump. As you go to 1 on g, from one side you approach what looks like -2, one side you approach -1, so as you get close to 1, g doesn't decide which place it's going to go. Okay, so no. So we'd want to say this is the limit as x goes to 2 of f of x over the limit as x goes to 2 of g of x. And can we do it?
Stop trying to trick me.
Stop trying to trick you? I'm trying to make you put your brains on. So
I thought that was the point.
it was the point. So what's happening as x goes to 2, f is getting close to, I don't know, like 1.4, 1.3, something like that, right? So this would be 1.3 divided by, no, right? And just say, you know, so, and in WebAssign you're going to say DNE, they even like use those letters, and I just realized I went off my screen, sorry. DNE, and I would like a little reason, like on your quiz, as the limit as x goes to 2 g of x equals 0. I don't need a complete sentence, I just need some way that you told me you get, this is the problem. That's not super hard, right? Okay. Alrighty, so going back to A for a second. As x went to 2, the part of that where we just looked at this, that was this point, right? Does it make sense that the value of the limit was the same as plugging in that number? You see what I mean by that? So the limit went to -1, right? Which is the same thing you'd get if you plugged -2 in. Was that true with this one right here? Is the value of the limit equal to what you get when you plug in -2? No, so when you plug in -2, you get 2, right? Because that dot's filled in up there. So, in general, as long as there's no sort of funkiness happening, like holes or stuff like that, the limits will equal what you get when you plug in that number. So like with functions that are, in this case, smooth and continuous. Here are some more properties that are pretty intuitive. Let's start with 7 and go back to 6 at the end. I don't know why I put 6 there. Anyway, okay, so what would something that looks like C, what would that look like as a function? A straight line, it'd be horizontal, right? So you'd have some sort of horizontal line. Okay, so y equals C, and there's a random point A, okay? What happens as the x's approach A? What do the y's approach? they approach C. So the limit thing is always asking about what happens to the y as that happens to the x. Does that make sense? And no matter where I put that a, as you approach that a, the y's are C, right? Does that make sense? Jimmy's giving it the I don't like it face.
I'm not sure if I'm agree. Should.
Okay. But the point is, if your function is C, C is a horizontal line, y equals C, and what happens to the y's as x is approaching any number? Well, the y's are always C, no matter what that a is. So the limit of a constant is just the constant.
Yeah, that sounds better.
Does that sound better? So limit of a constant is the constant. What does y equals x look like? It's a diagonal line. And that's called the identity function because x and y are always the same. If x is 1, y is 1. If x is 2, y is 2, right? So what happens as the x goes to a? What would the y value be at that a? A. So the limit as x goes to a of x is a. Which seems a bit silly, right? As x goes to a, x goes to a.
Is it always at that angle? Is it always one?
If it's the line y equals x, it's always that angle. If it was 2x, it'd be a little bit different, but then this would go to 2a,
Okay.
right? Like you could use the property where constants factor out. Okay. So x to the n looks different for different kinds of functions, but let's just sketch x squared. Okay, so there's my a value. Here's y equals x squared. So as your x approaches that a value, what would the y approach? In that case, it'd be a squared, right? Does that make sense? If I drew a cubic, it'd approach a cubed, right? If it was a quartic, it'd approach a to the fourth, right? So if x goes to a, x to the n is going to go to a to the n. So this seems a little, but all that's happening here is that a is getting plugged in for x, right? It's not more complicated than that. But the reason why kind of is the picture. And so if that's true for number 9, what do you think is true for number 10?
Equals n root x.
N root of a. And this is like assuming nth root of a is defined. Do you know what I mean by that? Like you couldn't square root -2,
Yeah.
right? Stuff like that.
Just one for the bachelor.
No, because we're just looking at real numbers. And so what these properties are kind of hinting at is that as long as there's no funny stuff going on, you can just plug this number in for whatever the x is. And I do mean that first word, as long as there's no funny stuff going on. So like for this first one, you could just say that this is equal to f of a to the n. And this one is the nth root of f of a. As long as there's no funny business. And by funny business in general, I mean like division by 0, rooting negatives, stuff like that, okay? So as long as no funny, plug in the number. That's what limits are. And the whole no funny business means the function actually is like a smooth curve or what's called a continuous curve at that point. But I think I actually did miss a property. So add a number 12, please. The one that I forgot is the limit as x goes to a of c times f of x. But didn't I, or maybe I had that in the previous thing. I had it above, never mind, I didn't miss it. That the constant can factor out. And then as long as there's no funny business, you can just plug the number into the function. But if plugging a number into the function yields division by 0, all these properties break down and fail. Okay, so if your denominator ends up being 0, stop, you do something else. And we'll get to examples like that. Okay, so I'm not going to assign any homework problems like this because... Did I skip? I didn't intentionally skip 11. I didn't skip 11. Okay. So this, we'll just do one this way in class. So what this is trying to sort of explain to you is that the reason you can plug numbers in is because of all of those properties. So if I was going to do this, the first thing in my head is I would say I'm going to find the limit as x goes to 5 of 2x squared. I'm going to take away the limit as x goes to 5 of 3x, and I'm going to add the limit as x goes to 5 of 4. In some sense, the limit does distribute, yeah. Or the limit applies to every term. And this officially is properties number 1 and 2.
Your constant vector that doesn't have an x.
Say that again?
You said on the last part, the one that doesn't have an x.
Yes.
You're still doing the limit of 4. What is that?
Okay, that's just going to be 4. As x goes to 5, the y is 4. Like if you were to look at what this looks like as a function and then find the limit graphically, that looks like a horizontal line with a y coordinate of 4. And as x approaches 5, the y goes to 4. Yep, that was that one that you were given the confused face, like the C one. The limit of a constant is just the constant. Okay, yes, Natalie?
What's the 1, 2?
The 1 and 2 are the properties that were used.
Oh.
So look at the list that you had on the previous page. It was the first 2 properties that said you could separate limits out that were added and subtracted. Does that make sense? And then there's a property that says that constants can come out, right? So it's going to become 2 limit x goes to 5 x squared minus 3 limit x goes to 5 of x. That was property number 3. And then it's just 2 times 5 squared minus 3 times 5 plus 4, or arithmetic 50 minus 15 plus 4, which is what, 39? That second one was properties 8 and 9. Anyway, the point is, this seems super tedious. What effectively, in the end, what happened? What did I do? You just plug in 5 for x, right? And that is the moral of the story. If there's no funny business going on, you can just plug in the number. Okay? Like, plugging in the number isn't going to yield division by 0, is it? We're not going to get rid of a negative. Okay, the limits work that way. As long as you don't have any funny business, you can just plug the number in. So like part B, take a look at that. Can you just plug the number in part B?
Yes.
Yes, so go ahead and do that and work out what it is. And part B, you might be a little bit more worried because it's a fraction, like maybe like a little bit concerned, but since plugging in -2 doesn't make that denominator 0, you're fine. It'd be like what Alexi Ripken would say, you're in business. So this would just be -2 cubed plus 2 times -2 squared minus 1 over 5 minus 3 times -2. So I got -1/11. I got that twice now. Do you guys agree with -1/11? Okay. So those are the easy ones. And it is true even if the functions look a little funky. Like this works with sines and cosines as well. Like as long as and even tangents and cotangents, as long as the number you plug in doesn't give you division by 0, it's okay to just plug the number in. Okay? So The harder thing is what happens if the denominator is 0 and what do you do then? So that property that I just stated is called the direct substitution property. If you have a polynomial rational function, you can just plug the number in. And that's actually true for trig functions, exponentials, logs, all sorts of stuff. As long as you don't do anything illegal or breaking your commandments, you can just plug the number in. So, but look at part A of example 3. Can you just plug 1 in?
No.
No. When you plug 1 in the numerator, you get 0. Plug 1 in the denominator, you get
0.
and crap. Remember how 0 divided by 0 is undefined? Okay. So we're going to go back to pre-calc for just a second, and it'll tell us how to find this limit, okay? I made my pre-calc kids do this. Some people hopefully made you do this too. Okay, so take the function y equals x squared minus 1 over x minus 1. And we're going to pretend that we're going to graph it. Okay, you could graph it a couple ways. You could plug numbers in, right? Let's just plug some numbers in for kicks. What do you get if you plug in 2? You get 3 over 1. So you get, when you plug in x equals 2, you get 3, right? So over 2 up, 1, 2, 3. Okay, you can't plug in 1, right? What about when you plug in 0? So you just get 1. Do you guys agree with his analysis there? Okay, we'll just plug in one more number. What if you plug in 3? I think you get 4. Do you agree with that? Okay. Okay, and we'll plug in just one more number on the other side. How about we plug in -1? 0.
0, yeah.
Okay, so what is that looking like? It's looking like a straight line, isn't it? Okay, and the question is just why is that true and what's going on in the middle? So when I did this in pre-calc, I didn't have them plot points, I had them simplify the function. Can you factor x squared minus 1?
Yes.
It factors into x plus 1, x minus 1, right? All over x minus 1. And so what does that simplify to? And there is the slight technicality, this is in your homework, that you have to add in that x can't equal 1 to state that those two things are equal. And so the reason for that technicality is technically you can't plug -1 into this, right? And that's implied because there's that denominator there, and the denominator is 0. So the way to say that you understand and remember that that was a restriction is you add that there. And if you were to draw this graph, you would just have an open hole there like this. And so how my students were taught to graph that is they were taught to graph x plus 1 and just leave a hole at this one value when x is 1. And if you were to plug in 1, the y would have been 2. Does that make sense? Okay, now look at that picture. What is the limit as x goes to 1 of x plus 1? 2. Okay, so this would be like if it were just the regular graph with no hole. What is the limit as x goes to 1 of that function we graphed? Because this technically, this picture with the hole in it is the graph of this function, right? As you approach 1, what does the y approach? 2. So that's how you attack limits that are 0 over 0. Is you find a function that the technical thing is that it agrees at all but one point. If I were to graph the function y equals x plus 1, it'd be the whole thing filled in, right? When I graph this thing, it's that line of the hole missing. They're the same except for that one point, right? So the way to find this limit is to say, okay, well, that's equal to the limit of the function x plus 1, x minus 1 over x minus 1, which then you simplify. And doing that simplification gets rid of the thing that's causing the problem. And then you can just plug the number in. And so what's that limit going to be? 2. So in that particular instance, 0 divided by 0 was 2. But the technical reason is because of those whole functions being equal everywhere except for 1 point. And the other thing is I have to be picky about this. It's not just because I'm being a meanie. You have to write limit signs every time, even though it's 6 characters, until you've actually taken the limit. You understand what I mean by that? Okay, we didn't take the limit until we plugged the number in. Okay, taking the limit is what we did when we input the number. So have we input the number in this step? We didn't put 1 in yet, did we? So the limit sign has to stay there. Had we put 1 in at this step yet? Like we did it right there, right? And then the limit sign goes away, you've done it. Does that make sense? But if you leave it out, technically, you've said that those two expressions are equal, which they're not unless you add in that restriction. So the point is, the limit thing is like an operation that you haven't done until you can plug that number in, so you've got to write it there until you've plugged the number in.
So even if you just work out
You've got to write it you've got to write it every time. And I'm not ever too picky about that. So just, you have to, when you're giving me solutions, be kind of neat and nice about them. When you're doing web design on your own, you can be as sloppy as you want. I don't care. Does that make sense? But I only make you do 5 problems written. Make those pretty. Does that make sense? Okay. Let's do another one. And as with these, the devil's in the details of a lot of them. Because this one involves a factor pattern you may have forgotten. So, can I just plug in 1? No. Okay, so 0 divided by 0 isn't 1. Shoot. Don't go cry in a corner. Can you, so we're going to have to leave the limit sign there. So one way to find these is to try factoring and seeing if the problem child, or the thing making the denominator 0, will cancel. This one is an example of that as well. Can you factor x squared minus 1?
Yes.
Yes, that's x plus 1, x minus 1. X cubed minus 1 is a bit tricky. Have you heard of the sum or difference of cubes formulas? Usually they're given as how to factor a cubed plus b cubed and a cubed minus b cubed. These are clever. And here's the factor pattern. This is a plus b, a squared minus ab plus b squared, a minus b, a squared plus ab plus b squared. Right, the point is factoring is hard. Like figuring out what stuff was multiplied together and then canceled is really pretty tricky. How could you prove that these were actually okay? Like, how do you know that they work? How could you check? You can multiply it out, and if you do that, you're going to get whole crap tons of middle terms canceling, and all that's left is first number cubed minus second number cubed. So let's do 1, and then we'll do the top one. So if I gave you like x cubed minus, say, 27, okay? That's the same thing as x cubed minus 3 cubed. Do you agree with that? Because 27 is 3 to the 3rd power, right? And so from there, the minus sign tells you which formula to use. So which formula do you use? The bottom one. So that's going to be x minus 3 times plus 3x plus, which is 9, right? And then how could you check if you're right? Multiply it out and you're going to get x cubed minus 27, okay? So using the same kind of pattern, how could you factor x cubed minus 1? And then x squared, right? Plus x and then plus 1. And those are hard to remember because they're not nearly as intuitive as the a squared minus b squared formula. So it's just something you're going to have to remember for the time being.
Probably just you don't use it very often.
You don't use it very often. No, you don't. And so that's why I think we should go over it, but they will come up on your homework and it will be on your quiz. Okay, I promise there'll be one example that uses them.
We should get them like a rolled up whiteboard next to them so they don't have to keep going down.
That, or they should just leave it down.
Yeah.
Okay, limit x goes to 1. Okay, can something cancel now? Yeah, the x minus 1s. And that should make you really happy because that's the thing that was causing the issue. Do you see what I mean by that? That's the part that was making that denominator 0. You see what I'm saying? So now that that's gone, you can just plug in your number and be happy. So now can you just plug in 1? Yeah, and your numerator is going to be, denominator is going to be 2. Okay. So one strategy, if you see something, is if you can factor it, factor it. Does that make sense? Okay. Another general strategy, what my friend Larry would call follow his nose, is just to use some algebra. As in like expand and simplify. So so this question, you can't just plug in 0 because the denominator is 0 and you dividing by 0 is bad, right? As it just doesn't work. Numerator is 0 too. So what could you do with h minus 5? You could expand it, right? So what is h minus 5 times h minus 5 equal to? H squared, minus how many h's? 10, plus 25, and then minus 25, all over h. Does that make sense?
Factor in H out.
And well, yeah, and the first 25's cancel, right? So that becomes the limit. H goes to 0, h squared minus 10h over h. And now can you cancel an h? So that becomes the limit as h goes to 0, h minus 10. And now can you plug in 0? Yes, and you get... Does that look like vaguely familiar?
The A plus H.
It's like the... Exactly. It's like the a plus h minus f of a thing we did in your quiz. It's just that instead of a, I plugged in the number -5. Okay? But that expression is going to come up again.
Was it called the difference quotient?
It's called the difference quotient, yep. I think the next one is awfully similar except for something is cubed, right? And cubing isn't as easy as squaring, is it? The next one is cubing, yes? And cubing is not as easy as squaring. So is 3 plus h cubed equal to 3 cubed plus h cubed?
No.
No, okay.
Good
Exclamation mark, angry face. Okay? No, okay, so it's not that easy. So you revert back to what you know. You're like, well, I know that cubed means I have that factor multiplied by itself 3 times, right? That's the basic definition. And I know how to multiply, so I can multiply those two first, right? That'll give me 9 plus 6h plus h squared times 3 plus h. That was a little fast, but does that make sense? Distribute the 3, distribute the h. And now can you do it again? Okay, so distributing just the 3 first, we'll have 27 plus 18h plus 3h squared plus 9h plus 6h squared plus h cubed. Okay, so that's going to be 27 plus plus 18h. Oh, no, not 18h. How many h's will I have? 27, thank you. How many h squareds? Okay.
Is 27 just 3 cubed? Couldn't you use the formula we used before?
You could, yes, there is a clever way to do that, and if you can figure it out, you're welcome to. I'm not going to go over it now, okay? Plus h cubed minus 27. So the answer is yes if you can figure it out, okay? I'm happy to tell you more after class, but I don't want to confuse anybody else with it. So all I did was plug in what 3 plus h cubed was, right? And now what cancels first? 27s, okay. The limit h goes to 0, 27h plus 9h squared plus h cubed. And to do that division by h, you have to have every single term have an h. See what I mean by that? Like everybody has to have h as a factor. So now can you divide by h? Yes, okay. And you get the limit h goes to 0, 27 plus 9h plus h squared. At this point in time, can you plug in 0? Yes. And 9 times 0 is going to be 0, right? 0 squared is going to be 0, so this will just be 27. But basically just algebra, right? Okay. And you can see that like a fourth power would be super evil and tedious, right? As well. Having to fourth power something would be really nasty. I probably won't make the power bigger than 3 just because it's going to be so much algebra and it just feels like a little bit much.
It's a time issue.
And it's a time issue, exactly. It's not like a you couldn't do it. It's like could you do it accurately and quickly, and that just takes too much time. Okay. What time is it? Okay, we're good still. Next we have things. So is it true, could you just say root t squared plus 9 equals t plus 3? No. You wish, okay? I wished too when I was in calculus for the first time, okay? So roots don't distribute, powers don't distribute, suck. Okay, which means psi in Swedish, so, you know. Well. So in this case, the common trick to apply is to use something called the conjugate. And often you use that when you simplified expressions like this. Or let's make it a little bit different. 1 over. You were asked to rationalize that denominator. And what did you multiply by to rationalize that denominator? Do you remember? 3 minus root 2 and 3 minus root 2. We're going to do the same thing here. It's just that instead of rationalizing the denominator, you're going to rationalize the numerator, which is a little bit weird, but you're going to do it.
This is why I'm opposed to rationalizing denominators.
I completely agree with you. I'm just unfortunately made to teach it a lot. So like I completely buy your argument because it makes why do that and not the other. I get it, yeah. So the conjugate here would be root t squared plus 9 plus 3 over root t squared plus 9 plus 3. Okay, yes?
Why are we rationalizing it?
Because when we do that, it will allow us to cancel the t squared. I know it's something you've never done before, because I myself didn't do it in your pre-calculus class, but it is done. As in, like, it can be done. Okay. When you multiply together those numerators, I'm going to do it the long way once and then never again because I'm lazy, okay? The roots times the roots makes t squared plus 9, right? Then you're going to have plus 3 roots of t squared plus 9 minus 3 roots t squared plus 9. Do you see what I mean by that? Like I'm just doing distribution. I'm sending that times that, that times that, this times this, and this times that. What's the last thing I'm going to have there? Minus 9. don't multiply the denominator out. And that would be my only hint to you, is only multiply the parts that are conjugates. Because your whole point is they cancel this t squared anyway, so for that you want it factored out.
That root term is 1.
Yep. And is it clear that the reason that conjugation is kind of special is it makes these roots cancel? And that's always going to happen as long as you've chosen to conjugate correctly? It was going to have one positive, one negative. So the roots cancel from the numerator. What else cancels? The 9s. So you've got the limit as t goes to 0 of t squared over t squared times root t squared plus 9 plus 3. And now can the problematic t squared from the denominator cancel? When that does cancel, what's left in the numerator? 1. Very good. Great. And now can you plug in 0? Division by 0 problem is fixed, right? So now when you input 0, what do you get? I think it's 1 over 6. Because what you get is 1 over root 9 plus 3, and root 9 is 6, right? Root 9 is 3, 3 plus 3 is 6. Yes, thanks. Root 9 is not 3. Oh my god, I can't believe I said that. So if you see a square root and you've got that denominator being 0 problem, try a conjugate. It doesn't always work, but it might. Okay, so like this next one. In the previous one, we conjugated the numerator, right? Here we're going to conjugate the denominator. And just to be clear, can you plug in 0 from the get-go? Like, because if you could, you should, right? But you can't because the denominator is 0 and so is the numerator, right?
Well, it would just be 0 plus 1, right? Oh, minus 1.
There's that minus 1 there. Yep. If there hadn't been that minus 1 there, then plugging in 0 would have been okay. Yep. Okay.
So if the negative 1 wasn't there, we just go with it, right?
Yes, if the negative 1 wasn't there, you could just plug in 0 and go with it. Yes, you definitely could. I will say that probably most of your homework problems won't be that easy. Does that make sense?
Yeah.
Okay. Okay. When those conjugates multiply together in the denominator, what do you get? Yes. 1 plus 3x minus 1. Do you agree with Rachel there? And then it simplifies to 3x. Okay. So there's still division by 0, but you can fix it because, yay, limit x goes to 0. Root 1 plus 3x plus 1 over 3. Woohoo! Now you can plug in 0. And you get 2/3. Spectacular. So really, that's like just a lot of algebra, right? The only new idea there is that this limiting process is getting close to 0, right? And that the functions that are the same except for one point have the same limits. But a lot of the details is that algebra, keeping track of signs, stuff like that. If you do conjugates, like as like a hint, if you had done 1 plus root 1 plus 3x times 1 minus root 1 plus 3x, be careful with parentheses. That will be 1 minus the quantity 1 plus 3x. Just be careful of stuff like that. Does Am I still before? Okay, I'm gonna go only until 11:30 and then we'll do some different stuff. Okay. How about this one?
Do you find a common denominator?
You find a common denominator. Do you guys understand what he means by that? You can't plug in 0 right now because you've got 1 divided by 0 and something else that's 1 divided by 0, right? Which maybe is infinity minus infinity, but that also consistently isn't one thing. So follow your nose, get a common denominator. And you could do it the hard way by multiplying the first fraction by the denominator of the second and vice versa. Or what you could notice is that this is the same thing as 1 over t minus 1 over t times t plus 1. You see what I mean by that? Just took out the greatest common factor. So what would you multiply this first fraction by to make it have the same denominator as the second? T plus 1, yep. Okay, they should just like leave that thing up or down and quit like.
That's what I'm saying, if they have like another whiteboard to use, then they wouldn't have to
know.
blow that thing up all the time to use the whiteboard.
Okay. So then this becomes t plus 1 minus 1 over t times t plus 1. Because you add fractions. Once they have a common denominator, the numerators add, right?
What is the t plus t?
Say that again.
Isn't it t plus t, not t plus 1?
It is definitely t plus 1. If it were t plus t, then the denominator would have been 2t squared.
Oh,
Right? Does that make sense, Devin?
yeah.
Okay. So the ones cancel, giving us t over t times t plus 1, right? And then what cancels next? T's. And then can you plug in 0? Yep, and you get what? You get 1. All right. And this next property that we had is one we actually had before. And we're going to use it to show that this next limit doesn't exist. So we had this property graphically that this is saying that the limit is L if the left and right limits both equal the same thing. Does that make sense? So the limits have to match up from both sides for the function to have a limit at that point. And we're going to use that to show that this limit doesn't exist. Okay, I'm going to do this 2 ways. The first way is I'm going to graph a picture. So if I graph the function absolute value of x over x, what happens when you plug in a number like 1? What do you get? 1. How about when you plug in 2? What's the absolute value of 2 divided by 2? 1. How about 3? And how about 0.5? Same. It's going to look like a flat line that is 1 up, right? And there's a hole at 0 because you can't do 0 divided by 0, right? What happens when you plug in negatives?
Then you get negative 1.
You get negative 1. Does that make sense? Because first you take the number like, say, negative 1 and you absolute value it, which gives you 1. And you divide by the original number, which was negative 1. Okay, so that's going to give you negative 1. So that's a graph of the absolute value of x over x. So what is the limit as x goes to 0 minus of absolute value of x over x? Negative 1. How about the limit as x goes to 0 plus 1? And as these are unequal, the limit does not exist.
We should just make up a new acronym, D and A.
Yeah.
Not agree.
Yeah, I could do that too, but I mean, it's like non-existent. I mean, D&E is so common, I don't want to change it, so you like don't start putting DNA and getting stuff wrong. Also, DNA is used for something else, right?
Yeah.
Okay. All right, so that's why that limit doesn't exist. I think we'll just go with that way for now. So how could you check and see without graphing? Because one way we check piecewise functions, like in the homework we did last time, was by graphing, right? How could you check this one without graphing if the limit exists?
Plug in 4 and see if they equal each other.
And the technical thing you're doing is you're finding the limit as x goes to 4 from the left. And that's got to equal the limit as x goes to 4 from the right. So you've got to actually say that, so I know that's what you're checking. Because part of math is using the language correctly. Does that make sense? And then you can just tell me what the stuff is. So as you go at 4 from the left, so the limit as x goes to 4 from the left, which part of the function do you use for that? If x goes to 4 from the left, that means x is less than or greater than 4? Less than. So which part of the function is for x is less than 4? The 8 minus 2x part. And no funny business, plug in 4, you get 0. How about the limit as x goes to 4 plus? Which part do you use there? You do root x plus 4, and that equals 0 as well. And actually 4 plus was kind of important there, because if this would have been 4 minus, the numbers would have, oh, so I wrote it because this should have been x minus 4, sorry.
We know what you meant.
Yeah, but I mean, it is important because I knew it was wrong. If this had been 4 minus, the numbers would have been a little bit less than 4. And that would have caused problems here, because a number a little bit less than 4 minus 4 makes a negative number. And you can't root negatives, okay? But the point is, since these two things equal, the limit as x goes to normal 4 is going to equal what? 0. Because both of those other limits are also 0. And had those limits disagreed, then you'd say, okay, the limit doesn't exist because blah doesn't equal blah. Or fill in the blahs with something. Okay. And then one more of these. This one's a little bit funky. So I gave you a line and a root function, and I said, how do you make those line up so the limit exists? So if the limit's going to exist, does it make sense that the limit as t goes to 2 minus of that weird function b of t has to equal the limit as t goes to 2 plus? Do you buy that? If it's going to exist, I said, okay, there's got to be a c so that it's going to exist. And if it's going to exist, that has to happen. So for 2 minus, from the left, which part do you use? Do you use the 4 minus 1/2 t, or do you use the root part? So you got the limit, t goes to 2 minus 4 minus 1/2 t. That's got to equal the limit. From the other side, you use the other part. There's no funny business, right? Can you just plug t in? No division by 0, right? When you plug 2 in, what do you get on this side? 3. How about the other side? You get root 2 plus c. And t2 is a, yeah, so you're just assuming that this hopefully will something like the square root. Can you solve that now? What do you do first? Square, so you get 9 equals 2 plus c. So c's got to be, And you could actually sort of check this by graphing. If you graphed the line and that root function with 7 plugged in for c, you're going to see that they actually match up at that point at t equals or x equals 2. But it was the same idea as the previous question, right? For the limit to exist, the limits from the left and right had to be equal to each other. The other thing that might be bothering you a little bit is that even though they're left and right limits, as long as there's no funny business, you can also just plug that number in. But the sidedness of the limit told you which part to plug it into. You see what I mean by that? The fact that this was 2 minus meant your t's are less than 2. That's how you chose to use this one. This one being 2 plus, meaning t's are bigger than 2. That's how you know to choose the root one. Because the root one is the part for just t's that are greater than 2. Okay. One more theorem, then you guys will have a break and you can work on some stuff. This theorem is pretty intuitive. So it's called the squeeze theorem. So you have a function f of x, crap, I made a typo. So anyhow, we're gonna fix it. So you have a function, 3 functions, f of x, g of x, and h of x. And they are equal. That relationship is true except for the case when x is possibly equal to a. And here's my typo. This should say f and this should say h. So you have some point A. There's the function h of x. There's the function f of x. And as you approach A, they approach this number L. Is that okay? Now, where does this function g live? G could be a straight line. Well, G just, it doesn't be a straight line. The point is it has to be in between those functions. Because this inequality says that, well, g of x has to be smaller than h of x but bigger than f. So g has to live in between those lines. And it could be a straight line, but couldn't it technically do something like this? Do you agree with that? That still holds that property? Is still the case that g is in between h and f? Okay? And so if you have this relationship that your g function is squeezed in between these 2 functions, and those 2 functions limit to the same place, the limit of the function that's squeezed has to also be the same place. By that? Okay, that's what it's called the squeeze theorem, because g is squeezed in between 2 functions, and as a result, its limit, as it goes to that value, has to be the same as the limits of h and f. If those limits didn't match up, you couldn't make any conclusions. But because they're assumed to match up, you said, okay, if that happens, then this other thing has got to happen too. And this often comes up with sine and cosine functions, because sine and cosine functions, they're stuck between 2 specific numbers, -1 and 1 specifically. So we'll have one example where we are given some information, and then one example where we have to find the functions it's sandwiched between. Okay? So I told you that this mystery function f of x is in between these 2 things. Okay? I want you to find the limit as x goes to -1 of it. So if this relationship is true, then the limit as x goes to -1 of 1 is less than or equal to the limit as x goes to -1 of f, which is less than or equal to the limit as x goes to -1 of x squared plus 2x plus 2. And then work out the ones that you can work out. Can you work out the limit of the constant? What's the limit of that constant 1 going to be? It's just going to be 1. Because even though x is going to -1, the y is always 1. Can you work out that middle limit? Do you know what f is? No, so leave that as a limit then. How about the upper one? going to be 1 minus 2 plus 2, isn't it? Okay. So your limit that you don't know is both bigger than or equal to 1 and less than or equal to 1. So what is the only option then? It's got to equal 1. You want to learn a fancy math symbol? These 3 dots mean therefore. Limit as x goes to -1 f of x equals 1 by the squeeze theorem. My book called it the sandwich theorem when I was in college because it's also sandwiched between 2 functions. I want you to know its name, and I think it has a pretty intuitive name because the function is squeezed or sandwiched. One student insisted on calling it the sandwich theorem with a funny accent because he was goofy. But that's not very hard, is it? I told you what the function was in between, and if you don't get that these limits match, you can make no conclusions, but you're probably going to almost always get that those limits match up. Okay, and if that's true, your number is both bigger than or equal to a number and less than or equal to the same number, then the limit must equal that number. The last one we'll do before breaking is one where you have to prove it. Okay? Like, does it make sense that you can't plug in 0? Because of the fact that you have division by 0 in that sign. But do you buy the fact that sine of 1 over x is in between +1 and -1? It doesn't matter what you sign, right? The graph of this thing actually is kind of like that weird oscillating function that does that like super squishy thing in the middle. But the point is the y values are always in between -1 and 1. Do you buy that? Okay. And the thing that you care about is x squared times that thing. So if this is true, isn't it true that -x squared is less than or equal to x squared sine 1 over x, which is less than or equal to x squared? Question 1 is, do you buy that? I multiplied by a positive number. Does it flip the inequality signs? No. I multiplied everything by the same thing, didn't I? That's going to preserve the inequality. Why did I choose x squared? What was present in my original function? The original function had x squared. I was trying to get that sandwiched between something. And here's why this is helpful. Find the limit of each piece. Limit as x goes to 0, -x squared. What is the limit as x goes to 0 of -x squared going to be? Not a trick question. It's going to be 0. Yep. How about the limit as x goes to 0 of +x squared? Also 0. So therefore, this limit also is 0. And the tricky thing there is the whole like showing it involves telling me what things is in between, saying that, okay, well those things is in between both go to 0, therefore this thing goes to 0. And the hard thing was to figure out what it was stuck between. Okay, so that's it for stuff I want to talk about today, like as in me personally. But what I would like you to do in the meantime, oh, should have made a typo, is try to take a quick 5-minute break and then try to work through the examples for the rest of the stuff. And some of them are hard, so I'll do a couple like hints and stuff for them on the board when you get to them, but I want you to find a partner and like work through these problems on the next sheet. And I'll walk around and check them and help you if you need help, okay?